Alright guys, we're going to talk about lesson 3, and I broke it into two parts, so there's going to be a 3A that you're going to watch, and then later you're going to watch a 3B. So let's first talk about 3A, which is trends in atomic radius. So, the atomic radius is the size of the atom. Basically what it is, it's the distance between two adjacent nuclei. So we have two nuclei here that are side by side, and it's half the distance. So this distance from the inside of the nucleus, the central of the nucleus, all the way to where the two atoms meet and overlap. That distance is the radius. For you, and for this class in particular, all you need to know is that the atomic radius is basically the size of the atom. These values are in your reference packet. They are located in Table S. Here is a little snapshot of what the top of Table S looks like. And the atomic radius is listed all the way on the right-hand side in picometers. That's what M stands for. So these values are going to be really, 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 really small. So what is the trend in atomic radius? Well, let's talk about going across a period. So as you go across a period on the periodic table, the trend actually decreases. Why does this happen? This happens because the nuclei have a greater nuclear pull, and that's because there are large positive charges in the nucleus. Remember, protons and neutrons are found in the nucleus of the atom. Protons are positively charged, neutrons have no charge, so the positive charges outweigh the neutral charges, and they're going to pull those electrons closer. So as we go from left to right across the periodic table, across a row or a period, the atomic radius is going to decrease. So let's look at aluminum and chlorine. Aluminum has a positive nucleus of 13, has 13 protons, and has a radius that is like this. Chlorine, on the other hand, is going to have a greater nuclear charge, pulling these electrons in closer because there's more protons in the nucleus. So let's look at the trend going down a group. Down a group, the trend actually increases. And why does that happen? That happens because there's a greater number of energy shells, and that's indicated by the period number. Remember, the further and further down you go on the periodic table, the more rings you add, or energy shells, you add around the nucleus of the atom. That causes the atom to get larger in size. So let's look at, these are elements in group 1. So if you're looking at lithium, which is in group 2, it has 2 rings where electrons can be found. Sodium has 3, so notice how sodium gets bigger, and the potassium gets even bigger than that because potassium has 4 rings where you can find electrons in it. So here's an overall shot of what the trend looks like. So the atomic size is going to decrease going from left to right across a period. Notice how all of the size of these atoms are getting smaller, and then they're all going to increase going down a column. So for our purposes, the smallest is going to be helium or fluorine, and then the largest is cesium. So how can you use Table S to determine the trends in atomic radius? I know a lot of you don't like to memorize things, so why don't we use the reference packet that Miss Christie and myself gave you to understand how this atomic radius looks. So what you need to figure out. So to figure out the trend in atomic radius, you can look at your Table S on your reference packet. So pick a row or group column and note the values of the elements. So what would that look like in a question? That would be like, for example, going across a period, what is the trend in atomic radius? So what we could do is we would look. So we're going to pick an element on the left side of the periodic table and pick another element on the right side of the same period. So we're going to pick period 2. So we're going to look at lithium on the left and fluorine on the right. And let's look at those values in the S table. So this is Table S, a snapshot of Table S. So lithium right here is 130 picometers, and fluorine here is 60 picometers. So you're going from 130 picometers directly across the period to 60 picometers, so that trend is decreasing. Very easy for us to see this just by looking at Table F. All right, let's look at a practice. Compare the atomic radius of a period 2 alkaline earth metal with that of a period 4 alkaline earth metal. Pause the video, answer this question, and then unpause it to find out what the answer is. All right, great. So what did you come up with? You should have came up with that the atomic radius of a period 2 alkaline earth metal is going to be smaller than that of a period 4 alkaline earth metal. Remember, if it's in period 2, it's going to have 2 energy shells around it, and if it's in period 4, it's going to have 4 energy shells around it. So obviously the period 4 alkaline earth metal is larger than that of a period 2 alkaline earth metal. So we're going to have to think about some things that we talked about a little while ago in the atom unit. So let's talk about ion size. So in the atoms unit, we talked about cations and anions. So let's talk about their radius. Ion size, so for example, metals. Their ion size is smaller than that of their atom size or their atomic radius. And this is because metal ions lose electrons to form cations. So if we look here, we have a sodium atom which has 11 electrons. It loses an electron to become an ion, the sodium ion, and look at the size. The size definitely decreases, and that's the same as if we look at the rest of the elements in group 1. Now here's a snapshot. On the right hand side we have the atom, and on the left hand side we have the ion. Notice how the atoms are all larger than the ion. The atom of lithium has a radius of 152 picometers. The ion is about 76. Notice that the size definitely decreased. Nonmetals is the same thing. So for the ion size for nonmetals, the ionic radius gets larger than the atomic radius. Why does that happen? That happens because metals gain electrons to form anions. So over here we have the chlorine atom. It's going to gain an electron, so instead of having 17 electrons, it's now going to have 18. And look at how the size of the ion increases and gets larger. Same thing happens in this picture as we look at the ions over here. So for the fluorine ion, chlorine ion, and the bromine ion, and then the atom on the right-hand side. The fluorine atom has an atomic radius of 72 picometers, and the ion's radius is 133. There's definitely a gain in size there. So here's a picture that shows the overall trend between ionic radius for metals on the left and nonmetals on the right. So remember, metals, their ion is smaller, and for nonmetals, their ion is larger. So let's look at some check your understandings. Now remember, when you come into class tomorrow, we're going to talk about these first. So what is the trend in atomic radius going down a group? And then also I want you to think about and answer the second question, which is why does this trend occur down a group? Remember, this will conclude lesson 3 part A, and lesson 3 part B we'll talk about later.